Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk about periodic motion and simple harmonic motion. Periodic motion is a type of vibrational motion, or sometimes called oscillatory motion. During this type of motion, there is one point in the object's path where there is no net force. At that point, the object is said to be at equilibrium. When the object is pulled or pushed away from the equilibrium position, the net force becomes non-zero and always pulls the object back toward that equilibrium position. If the force that restores the object to its equilibrium position is directly proportional to the displacement of the object, the motion is called simple harmonic motion, or SHM, and the force is called the restoring force. During simple harmonic motion, the acceleration of the object is also directly proportional to the displacement, but it's always in the opposite direction of the displacement. That's also true for the force. Some important terms to think about while we're talking about simple harmonic motion include the period, which is the time required for one complete cycle, and the amplitude, which is the maximum displacement of the object from the equilibrium position. We're also going to talk about Hooke's law. Hooke's law, important topic, that says that the restoring force due to a spring is proportional to the length that spring is stretched. This force acts in the opposite direction of the displacement. What this means is that the bigger the force that's used to move an object from the equilibrium position, the more it will stretch. Hooke's law can be stated in an equation. It looks like so, where F is the restoring force. K is called the spring constant. It's a measure essentially of the string's strength. And X is the displacement. Now notice that negative sign. That negative sign tells you that the force is going to be in the opposite direction of the displacement. So let's look at an example problem. It says a spring is attached to the ceiling and has a block of mass 3 kilograms attached to the other end. The displacement of the spring when at equilibrium is 0.3 meters. We're on Earth with G is 10 meters per second square. What's the value of the spring constant for the spring? So we're saying that we have a spring, maybe like so. Now right now there's no weight attached to it, so that's its normal length. Well, when we attach a weight, the spring lengthens a little bit. So let's note that this is the original length, and then once we add the weight, the spring stretches a little bit. And this distance of stretch when the weight is attached is 0.3 meters. That's our displacement. We're attaching a 3 kilogram mass right here. We want to know the spring constant. Well, to calculate that spring constant, we're going to use Hooke's law. F equals negative kx. We're going to solve that for k. So we're going to divide both sides by x. Like so, that's negative k. Now remember that in this case, the displacement is down, so that displacement is going to be a negative number. So we're going to put, first of all, the force. The force is not going to be the mass, it's going to be the weight. So the weight of that 3 kilogram object is 3 times g, 3 times 10 in this case. So the weight is 30, so this is our force, 30 newtons, over our displacement, which is 0.3 meters down, so that's negative 0.3 meters, and that's equal to negative k. So once we divide that out, k is going to be equal to positive 100 newtons per meter. So that's our answer to part A. Now part B wants to know what's the displacement of the spring away from the equilibrium position if the system is moved to a planet with an acceleration due to gravity of 4 meters per second square. So now we're not on Earth. Now we're somewhere else. The gravitational field strength is less. We use the same spring, the same mass, and we want to know what the displacement away from equilibrium is going to be. Well, in this case, we're going to go back to Hooke's law. This time we're going to solve for x. So x is going to be equal to F over negative k once we divide that out. So our force on this new planet is going to be the mass, 3, times the acceleration due to gravity, 4. So the new force is going to be 12 newtons. K is still the same, 100. It's negative K here, newtons per meter. Our displacement is going to be in the downward direction. We're going to divide 12 by negative 100, and we're going to get X equals negative 0.12 meters. And again, that negative means that the spring is going to stretch in the downward direction. But that's our answer to part B. Now, some examples of simple harmonic motion include masses attached to both vertical springs and horizontal springs. We're assuming here that we're going to ignore friction. We can calculate the amount of elastic potential energy stored in a spring using this equation, where U sub S is the elastic potential energy. It's equal to 1/2 times K. Again, K is the spring constant, and X here is the displacement away from the equilibrium position. So 1/2 Kx squared. We can also calculate the period of the mass on the spring using this equation. So 2 pi times the square root of the quantity of mass, m, over K, spring constant. Notice that the period here does not depend on the displacement. We can also calculate the position of the object at a specific time using this equation, where X is the position, A is the amplitude. Amplitude is the maximum displacement, times the cosine of the quantity, 2 pi times F for frequency, measured in hertz, and time, measured in seconds. So we can also talk about a mass on a horizontal spring. And we'll come back to that point here in just a second after we look at a picture. So here's a diagram of a mass on a horizontal spring. At position number 2, the object is at equilibrium. So at this point, the spring is not stretched. At this point, the displacement is 0. There is no restoring force acting at that point, and the acceleration of the object would be 0 at that point because there's no net force acting upon it. Well, now let's say we take the object and we stretch it over here to the right. So we stretch the spring. So now we're at our maximum displacement. Remember, we call that maximum displacement the amplitude. And now we let that, we let it go. We let the object go. At the moment we let it go, the speed is going to be 0. But the acceleration is going to be maximum, because at this maximum stretch, the restoring force is going to be the greatest. That restoring force is the maximum net force acting on the object. When there's more net force, there's going to be more acceleration. Remember, the acceleration is always going to be in the direction of the equilibrium position. So once we let this go, it's going to begin to accelerate back toward the equilibrium position. Once it goes back to the equilibrium position in our second picture, at that point, there's no net force acting on it. Its displacement is 0. Its speed at that point now is going to be at its maximum speed because it's accelerated all the way to this point. But it's not going to stop at this point. It's going to have an inertia. It's going to continue to move past the equilibrium position and toward the left. Well, when it does that, the spring begins to be compressed. And now there's going to be a restoring force that's going to act in this direction. Now the acceleration is also going to act in this direction. And the speed begins to decrease. Well, that's going to continue until the object stops. So at its stopping point, it's going to be at its maximum negative displacement. Notice that it's a negative amplitude. It's going to stop at that point. So its speed is going to be 0. At that point, it's going to have maximum acceleration because the restoring force is going to be at a maximum, pushing back toward the equilibrium. So once it gets to that point, instantaneous, it's going to start to move back. It'll move back toward the equilibrium position going in this direction, and we'll repeat over and over and over and over again. Remember that in simple harmonic motion, the restoring force and the acceleration are going to be proportional to the displacement. So this is what a position versus time graph for simple harmonic motion might look like. So let's say the object starts here. So it's starting with a stretch spring to the right. It's at its maximum amplitude. We let that object go. Notice it starts to move back toward the equilibrium position, which is x equals 0. So here, it's back at equilibrium, but its inertia carries it on back further to the left. The spring starts to compress. At this point, it's at its maximum negative amplitude, its maximum negative displacement. So that's at half the period. Well, now it's going to be pushed back toward the equilibrium position. It's going to start to accelerate back toward the right. It's going to pass through, at this point, back through the equilibrium position, but it's not going to stop. It's going to continue to move toward the right. The string is going to continue to stretch, and here it finally returns back to its original starting point. So notice the time between here and here is 1 period, the time for one complete cycle. And then it's just going to return and repeat again and again and again and again. That's simple harmonic motion. So here's another sample problem. So again, we have a mass attached to a horizontal spring. We know K is 78 newtons per meter. The mass slides along a frictionless surface. We're also assuming there's no friction within the spring. And it's stretched 25.53 centimeters from equilibrium. So this is the amplitude, the maximum displacement. And then it's released. First of all, we want to find the total mechanical energy of the system. We want to find the speed of the mass when it has a displacement of 3.63 centimeters. And we want to find the maximum speed of the mass. So first of all, let's find the total mechanical energy of the system. Remember, mechanical energy is the sum of the kinetic and the potential energy. At the maximum amplitude, all of that mechanical energy is going to be in the form of elastic potential energy. So to answer part A, we can use elastic potential energy equals 1/2 kx squared. So 1/2 times 78 newtons per meter times x squared. Now we want to do x in terms of meters, not centimeters. So let's convert that over to 0.2553 meters. Don't forget to square. All right, so once we do the math on that, we end up with an elastic potential energy, and I'm going to write it up at the top here, of 2.54, and that would be joules. So that's the total mechanical energy of the system. All right, in part B, we want to find the speed of the mass when it has a displacement of 3.63 centimeters. So now it's moving back, let's say it's moving back toward the equilibrium position. Its maximum amplitude was 25.53 centimeters. But now it's closer. It's closer to the equilibrium position, and it only has a displacement of 3.63. As it's moving from here toward here, a lot of that elastic potential energy is being converted into kinetic energy. And that kinetic energy is going to allow us to find the speed. So at this point, 3.63, first of all, we want to find how much elastic potential energy it still has at that point. So we can go US equals 1/2 times K, 78, times x squared. So here x is going to be 0.0363 meters squared. So we do the calculation, and we end up with an elastic potential energy here of 0.0514 joules. So that's how much elastic potential energy the object has at this particular displacement. But remember, this is the total energy of the mass, the total energy of the system. So if this much is elastic potential energy, then 2.54 minus 0.0514 is the amount of kinetic energy that it possesses at that point. So let's go 2.54 minus 0.0514. And we end up with a kinetic energy of 2.4886 joules. Well, remember that kinetic energy equals 1/2 mv squared. So let's solve that out for V. So when we solve K equals 1/2 mv squared out for V, we end up with 2K divided by M square root equals V. So if we plug in what we know, the square root of 2 times K, remember K here is 78. Oops, let me back up there. K here is not the spring constant. This K we're talking about is the kinetic energy. So it's going to be 2.4886 joules all over the mass. The mass of our object was 0.766 kilograms. So let's do the calculation. All right, once we complete the math there, we end up with a velocity of 2.55. And remember that velocity, it's always going to be moving toward the equilibrium position. So 2.55 meters per second, and that's toward the equilibrium position. Our B only asks us for speed, so really 2.55 is enough. Now, the final thing we want to find is the maximum speed. Same basic idea that we just used, we'll use for part C. At the equilibrium position, the amount of elastic potential energy is 0 because the spring isn't stretched at that equilibrium position. That means that all of the mechanical energy at that point has to be kinetic. Well, we found out in part A that we have 2.54 joules of total mechanical energy, which means at the equilibrium position, K is equal to 1/2 mv squared, which is equal to 2.54 joules. So again, we're looking for the speed, and this is the speed at the equilibrium position where the maximum speed will always occur. Let's solve K equals 1/2 mv squared again for velocity. So that's going to be 2K divided by M square root equals V. Let's plug in what we know. So our total amount of kinetic energy at that point, at the point of highest speed, is 2.54 joules. We're going to divide that by the mass of our object, 0.766, and that's in kilograms, and we'll do the math. And we end up with a speed, a maximum speed of 2.58 meters per second. Now, that's not much higher than we got in part B, because in part B, the object was already pretty near the equilibrium position. So again, that's an example problem for a mass on a horizontal spring. Now here's another sample problem 2, mass on a horizontal spring. All right, part A, problem 2 is very much like some of the parts we saw in problem number 1. Here we have a mass, it's 0.0750 kilograms, attached to a spring with a spring constant of 400 newtons per meter. We want to know the maximum speed of the block if the amplitude, and remember that's the maximum displacement, is 6 centimeters. Assume the spring is an ideal spring. So first of all, let's find the total amount of mechanical energy in the system. And to do that, we're going to use 1/2 kx squared. And remember that all of the mechanical energy is elastic potential energy at the maximum displacement, at the amplitude. So US is going to be equal to 1/2 K, 400 newtons per meter, times, in this case, the amplitude squared. Well, the amplitude is 6 centimeters. So 0.06 meters. We can't forget to square that. So let's do the math. And we end up with a total elastic potential energy at maximum amplitude, in this case a total amount of mechanical energy of 0.720 joules. So that is the total amount of mechanical energy in this system. Well, we're looking for the maximum speed. Well, remember the maximum speed occurs at the equilibrium position, when all of that mechanical energy, instead of being potential, is kinetic. So we're going to use K equals 1/2 mv squared Again, we're going to solve that out for V. So 2k over m square root equals V. So in this case, 2 times k. Here k is the kinetic energy, which is going to be all of the energy of our system, the mechanical energy, which is 0.72. Divided by the mass. The mass of our object is 0.0750 kilograms. We're going to take the square root of that whole quantity. And we end up with a speed of 4.38 meters per second. So that's the speed of the object as it crosses this equilibrium position. That's its maximum speed. Maximum speed is always going to occur at the equilibrium position. Now, part 2, we want to know what's the speed of the oscillator when it's located 3 centimeters to the right of the equilibrium position. Assume that the amplitude of the oscillations is still 6. Some of you are going to fall into a trap. Some of you are going to say, well, it's halfway there, so its speed is going to be half of the maximum speed. So you would write down 2.19 meters per second. The problem is you would be wrong. And the reason you would be wrong is because the restoring force is not linear. The restoring force is higher at maximum stretch and decreases dramatically as the object moves back toward the equilibrium position. So to find the speed at 3 centimeters of displacement, first of all, we need to find out how much potential energy the object has at that location. So we're going to use US equals 1/2 kx squared. So again, our K is 400 newtons per meter. And our X here is going to be 0.03 meters squared. So let's do the math. So once we do the math, we find that at 3 centimeters of displacement, the object has 0.18 joules of elastic potential energy. Well, the total mechanical energy of the system, though, is still 0.72 joules. So if we go 0.72 minus 0.18, we end up with 0.54. So that means at this point, the object has 0.18 joules of elastic potential energy, but it also has 0.54 joules of kinetic energy. So now we're going to use this 0.54 joules of kinetic energy, and we're going to set that equal to 1/2 mv squared, and we're going to solve for the speed. So we're going to say K equals 1/2 mv squared. Again, solve that out for V. So V is going to be equal to 2 times K over m square root. So in this case, we're going to have 2 times our kinetic energy, 0.54 joules, divided by the mass of our oscillator, 0.075 kilograms. We're going to take the square root of that whole quantity. So let's do the math here. 0.54 times 2 divided by 0.075, and then take the square root of that whole quantity. So we end up with a speed, and our answer to part B, of 3.79 meters per second. So at halfway back to equilibrium, the speed is 3.79. All the way back, the speed was not that much greater than that. All right, so let's go back to part C now. On part C, what is the total mechanical energy of the oscillator spring system? So we already answered that question. The answer to that question is 0.720 joules. We find that by finding the elastic potential energy at maximum amplitude, or we could find the kinetic energy that the object has at equilibrium. Finally, we want to find the period of the oscillator. Now remember, when we're talking about a mass on a spring, to find the period, we're going to use an equation which is provided for you on your AP Physics 1 formula sheet, and it looks something like this. Period equals 2 pi times the square root of m over k. So our period in this case is going to be equal to 2 pi times the square root of the mass of our oscillator, 0.0750 kilograms over K for our spring, and here K is the spring constant of 400 newtons per meter. So if we do the math, 0.075 divided by 400, let's take the square root of that quantity and then multiply by 2 pi. And as long as all your units are in newtons and meters and kilograms, the period is going to come out in seconds. So we end up with a period of 0.0860 seconds. All right, so that's practice problem number 2. Now, finally, we're going to look at some problems with a mass on a vertical spring. So here's some information about a mass on a vertical spring. So in this picture, the mass is at equilibrium. At this position, the spring is stretched a little bit, but the weight of the box is equal but opposite to the force pulling upward in the spring. So it's not going to move on its own from there. So in the second picture, we grab onto the object and we pull it down. We're holding it at this point. So at this point, the weight is acting down, but there's a restoring force acting up, back toward the equilibrium position. And that restoring force is greater than the weight. So once we let it up, the force is going to be at its maximum on the way up. At the instant we let it go, it has no kinetic energy. All of that energy is potential. And we can calculate that using the equation we used a minute ago, 1/2 kx squared equals the elastic potential energy. At the instant we let it go, the velocity is 0. But right after that, it starts to accelerate. And there's going to be an acceleration in the upward direction. And the object is going to start to move back toward the equilibrium position. It's going to get faster and faster and faster. But as it gets closer to equilibrium, the restoring force decreases in magnitude. The acceleration decreases in magnitude. By the time it gets back to equilibrium in this third picture, it's going at its maximum velocity. At this point, the weight of the box acting down and the restoring force acting up are balanced. So there's no net force. Therefore, there's no acceleration at this point. The kinetic energy is at its maximum because the velocity is at a maximum. And at this point, there is no elastic potential energy because the spring is at its equilibrium position. The box doesn't stop at this point, though. It has inertia, so it continues on past the equilibrium position. Now the spring starts to compress, and that kinetic energy is now slowly converted into elastic potential energy in the compressed spring. So now the acceleration is actually this way. The velocity starts to slow down. Eventually, the spring will compress in all the way, and the box will stop. The object will stop moving for an instant. So at that point, its velocity is 0. The net force is acting down, back toward equilibrium. It's stopped, so the kinetic energy is 0, and it has maximum elastic potential energy. At that instant in time, its acceleration is also going to be at a maximum back toward the equilibrium position. So it's going to start to move back this way. Once it gets back to equilibrium, once again, its velocity will be at a maximum. At equilibrium, there's no net force acting on it, so it'll be 0 net force. Its kinetic energy will be at a maximum because it's moving as fast as it can. And at that point, since the spring is at the equilibrium position, there's no elastic potential energy. Again, it will continue past that equilibrium position, and then we'll start back over with the first picture. So that's sort of the basic idea of how a mass on a vertical spring works. This is simple harmonic motion because the size of the restoring force is proportional to the displacement. So here's what a problem might look like on simple harmonic motion with a mass on a vertical spring. All right, so here we have a mass, a 0.25 kilogram mass attached to a vertical spring. When we attach it, the spring stretches 0.052. The system is then placed horizontally on a frictionless surface and set into simple harmonic motion. what is the period of the oscillations? On a problem like this, we first of all have to find K. And once we know K, remember that the period of a mass on a spring is 2 pi times the square root of m over K. So we know mass, we know pi, we need to know K. So to find K, we're going to think about the vertical part of this problem. So here's the spring, it's unstretched. We put our mass on it, and it stretches down a distance of 0.052. Using that and Hooke's law, F equals negative kx, we can calculate K. So let's solve that out for K. Negative K is going to equal F over x. Plug in our variables. So negative K is going to be equal to the force. The force here is going to be the weight of the object, the weight of the mass. So we're going to go 0.25. We're going to use 10 for G. So 0.25 times 10 is going to be 2.5 newtons. We're going to divide that by the displacement, which is negative 0.052 meters. We divide that out, and K is going to equal 48.1. And that's 48.1 newtons per meter. So that's K. So now that we have K, we can plug into T equals 2 pi times the square root of the mass of the object, 0.25 kilograms, divided by the spring constant, which we just found to be 48.1 newtons per meter. We do the math on this, calculate it out, and we get a period of 0.453 seconds. And remember, the period is the time it takes for one complete cycle. All right, hope that helps. All right, we're also going to talk about a simple pendulum as an example of simple harmonic motion. For small displacements, angles of 15 degrees or less away from the vertical, a pendulum exhibits simple harmonic motion. It acts as a simple harmonic oscillator. A simple pendulum is essentially just an object, a small mass, sometimes we'll call that the pendulum bob, suspended from a wire or string of negligible mass. And we'll look at some of those in a picture in a second. We assume typically that the cord doesn't stretch and that the mass of the string is small enough that we can ignore it. The back and forth motion resembles simple harmonic motion. There's a restoring force here too that's proportional to the displacement, and we can find that restoring force using this equation. So F is the restoring force. It's equal to negative m, the mass, times g times the sine of theta. And this theta is the angular displacement away from the vertical. We'll see how that works in a minute. We can also calculate the tension in the rope or the pendulum string or cord using this equation. Tension equals mass times acceleration due to gravity times the cosine of that angular displacement away from the vertical. So let's go back to our picture. So in this picture, we see the vertical in green. This is our angular displacement of theta. So if we wanted to find the restoring force, notice we've drawn a little triangle here. We took the weight, this is the weight right here, of the pendulum bob, and we broke it into two components. One component going along the string, that's our tension component, and one component acting back toward the equilibrium position. So if we wanted to solve for the restoring force component, we could use sine. And we would say the sine of our angle theta is equal to the opposite side, which is the restoring force, over the hypotenuse, which is the weight, which we're going to call that mg. So that means that the restoring force is going to be equal to mg sine theta. And remember, that's always back toward the equilibrium position. That's why we saw in the equation a minute ago the negative sign. We can also calculate this tension component using the cosine. So the cosine of our angle is equal to the adjacent side, which is our tension component, over the hypotenuse, which is mg, which means that the tension in that cord is going to be equal to mg times the cosine of our angular displacement, of our angle theta. So that's tension and restoring force. Now, we also have an equation for the period of a simple pendulum. And that's what we're looking at right here. So the period, the time to go from this point all the way through equilibrium up to the maximum height over here and back. That's one period. And to calculate that time, 2 pi times the square root of L is the length of the pendulum, and G is the acceleration due to gravity. So notice that the period is not related to the angle of theta. It's also not related to the mass of the pendulum bob. The period is determined by the length of the string and the acceleration due to gravity. All right, so here's a sample problem involving pendulums. So we have a pendulum bob of mass 2.02 kilograms, and it's displaced from equilibrium by an angle of displacement of 10 degrees to the right. So we're saying that this angle is 10 degrees. First of all, we want to draw a free body diagram to show the forces acting on the bob. And you want to recall that on an AP physics test, you don't want to show components. You want to show actual forces. So let's take our mass. One of the forces that we know that acts on our pendulum bob is the weight. And we know that weight always acts straight down. So that's weight. We could label it as W or mg. And then the only other force that we have is the tension in the string, which acts sort of up along the string like so. And we'll label that T. You might also see it labeled as F of T. That's it as far as our free body diagram goes. Next, we want to know the magnitude of our restoring force. So now we are going to do some components. So let's erase our free body diagram. And what we want to do is now we want to draw in our weight. So this represents the weight. And we want to break that weight into two components. One that acts along the string. And that's really terrible. And one that acts perpendicular. This is supposed to be a 90-degree angle right here. So this component is going to represent the tension in the string, and this component is going to represent our restoring force. So to find that, we first of all need to know the weight. We have the mass. So let's go 2.02 times 10 to get the weight. So the weight's going to be 20.2 newtons. And to find the restoring force, we're going to think of this as angle theta. It's the same as this angle. So to find that restoring force, we're going to say the sine of that angle, the sine of 10, is equal to the restoring force, the opposite side, over the hypotenuse, which is the weight. So if we say 20.2 newtons times the sine of 10 degrees, we end up with 3.51 newtons. So our restoring force, 3.51 newtons. And that's toward the equilibrium position. To find the tension, we're going to use cosine. So we're going to say the cosine of 10 is equal to the adjacent side, T, over the weight, 20.2. So we're going to say the cosine of 10 times 20.2. And we end up with a tension force of 19.9 newtons. And that's along the string. Next, if the length of the pendulum cord is 52 centimeters, what is the period of the pendulum? Remember that the period of a pendulum, and here we're using T for period, not for tension, is equal to 2 pi times the square root of L over G. So T is going to be equal to 2 pi. Let's try that again. T is going to equal 2 pi times the square root of the length. Let's use that length in meters. So 52.52 meters over G, which we're going to use as, we'll just use 10 as G for right now. So 0.52 divided by 10. Take the square root and then multiply by 2 pi. And we end up with a period of 1.43 seconds. And then finally, it asks for the frequency. You probably can't read this very well on your screen, but it's the frequency. Well, remember that the period is equal to 1 over the frequency. They're inverses of each other. So our frequency is going to be 1 over our period, which in this case is going to be 1 over 1.43 seconds. So 1 divided by 1.43. So we end up with a frequency of 0.699. And that's, we could write it as S to the negative first power, or we might just write it as hertz. 0.699 hertz. All right, that's the pendulum practice problem 1. All right, so here's our second pendulum problem. So we have a pendulum of length 1.2 meters. The pendulum bob has a mass of 2 kilograms. It's displaced 12 degrees away from the vertical and to the right. We want to know how much potential energy does the pendulum have at its highest point above the ground. So we're looking here for gravitational potential energy. So let's say we have a vertical. So our pendulum was here, and now we moved it away from that vertical, and our angle is 12 degrees. All right, so as we moved it to the right, we also lifted it. So I'm going to draw a horizontal line over like something like this. And I want to calculate this length right here, the length from this point to this point. And we'll see why that's important in a minute. But remember, the length of the pendulum string is 1.2 meters. So that's the distance from here to here. So I could use cosine to find my distance. I'll just label this distance as x for right now. So I'm going to say the cosine of 12 equals adjacent x over hypotenuse 1.2. So if I do the math on that, x is going to equal 1.17 meters. So the distance from here to here is 1.17. Well, when the pendulum was sitting down here at this equilibrium position, this whole length from here to here was 1.2. Well, what that tells me is that we lifted, as we moved the pendulum to the right, we lifted it 1.2 minus 1.17, or 0.03. So we lifted the pendulum to a height of 0.03 meters. Well, from that, we can calculate the gravitational potential energy. Because remember that UG equals mgh. So in this particular problem, our mass of our pendulum bob is 2 kilograms. We're going to use 10 for gravity. And we lifted it to a height of 0.03 meters. So when we do the math on that, we end up with a gravitational potential energy of 0.6 joules. And with sig figs, we're going to write it as 0.600 joules. All right, part B wants to know, what is the pendulum's speed when it reaches the equilibrium position? Well, we know that when it gets to equilibrium, all of the potential energy that it had at the top is now kinetic. So we're going to set the kinetic energy equal to 0.6, the total mechanical energy of the system, and we're going to set that equal to 1/2 mv squared. We know the mass. So we've got 0.6 joules equals 1/2 times the mass of 2, and that's 2 kilograms times v squared. Well, 1/2 times 2 is 1. So essentially, we're just going to have to take the square root of 0.6, and we end up with 0.775 as our speed, and that's 0.775 meters per second. Let's put a 0 in front of that. All right, then we want to find the period of our pendulum. Well, remember that the period of a pendulum is dependent on just 2 things: the length of the pendulum string and the gravitational force. So T equals 2 pi times the square root of length over G. So in this particular problem, that's 2 pi times the square root of the length of the string, 1.2 meters, over gravity, and we'll just use 10 meters per second square. So if we do the math on that, 1.2 divided by 10, take the square root, and then multiply by 2 pi, we end up with a period of 2.18 seconds. Next, we want to find the restoring force. So to find the restoring force, we need to draw this out a bit. So let's make some space up top. So let's say here's our vertical. That's not vertical at all. Let's try that again. So that's sort of a vertical. Our pendulum is over here. This is an angular displacement of 12 degrees. To find that restoring force, we're first of all going to draw in the weight straight down. We're going to break it into a component along the string and then a component perpendicular to that. This component is going to be our restoring force. It's going to push the pendulum bob back toward equilibrium, and this component is going to be the tension. This angle is the same as this angle, 12 degrees. This is the weight. So if we want to find the restoring force, we're going to use the sine function, and we're going to say the sine of 12 degrees is equal to the opposite side, which is our restoring force, over the hypotenuse, which is our weight, which is 2 times 10, 20 newtons. So let's go the sine of 12 times 20. And we end up with a restoring force of 4.16 newtons. And that's back toward equilibrium. To find the tension, we're going to use the same diagram, and we're going to use the cosine function. So we're going to say the cosine of 12 equals the adjacent side, which is our tension force, over the weight, 20 newtons. So the cosine of 12 times 20 is 19.6. So it's 19.6 newtons acting along the string. Finally, we want to find the frequency. Remember that frequency and periods are inverses of each other. So the frequency is 1 over the period, which in this case is 1 over 2.18 seconds, which comes out to be F equal to 0.459 hertz, or cycles per second. So that is pendulum problem sample 2. I hope that helps.